Then, all right, Sahar, fantastic. Looks like it's working. So over to you.
Okay, can you see it's moving? Just to make sure it's moving, working. Okay, cool. Okay, so yeah, thank you again for the invitation to this talk. I'm really excited to talk about this work because I had so much fun working on it, and it's been on like currently under review. So I hope you also enjoy today's talk with this new paper. So before I start, I would like to give a conceptual high-level overview or summary that I think, in my opinion, summarizes some interesting and important LLM security aspects. So, like, conceptually, I think we used to have a static paradigm of ML models. Like, when thinking about classifiers or even previous generative models, we can observe that the output is generally a non-interactive process. So attacks such as evasion attacks or even misusing or abusing a language model or generative model, they are computed or optimized offline and then fixed during distribution. And also attacks in this second example here could take the form of exploiting one model to attack another model and so on. But I think now, this year and last year, we have chatbots and applications based and built on them that are more dynamic. So, for example, in applications, the input to the model may vary at test time, depending on the retrieved input or the user's queries. And the output of the model is also interactive and sometimes multi-stage. These factors also mean that the same attack can vary from one chat session to the other, or also from one user to the other. So extending this trend and looking forward to future applications, so it seems plausible now that instead of having one model, we might have a network of models or agents that are autonomously interacting in some real-world tasks. So the motivation of this work is that, given these new perspectives, we need to adjust our evaluation accordingly. So LLMs are trained mostly in an unsupervised way. So most of the training is done in an unsupervised manner. And additionally, most of earlier NLP benchmarks are static in nature, such as maybe question answering system or multiple choice questions that the answer is just one-step process. But now LLMs are being used in interactive real-world tasks that may require assessing complex situations and may require that the agents act on their environment. And therefore, given that, I think we need new evaluation benchmarks that simulate such complex setups. So we chose negotiation towards this, and we use specifically interactive multi-agent negotiation games. So our choice of negotiation is motivated by several factors. So from a practical perspective, I think negotiation and cooperation play a key part in our everyday communication. And when we use agents for the simplest tasks, such as scheduling appointments, they should make correct inferences about the user's priorities, and they should be able to rank different offerings accordingly. So in this example here, if I ask the agent to schedule an urgent appointment, this should be translated to the earliest possible appointment, for example. And also, in addition, AI agents and models are used in negotiation agents, even in real-world applications, and sometimes in autonomous negotiations. And from a technical perspective, I think like negotiation games in general are an excellent testbed to evaluate LLM's reasoning, as I will show later in the rest of my talk. So our game takes inspiration from role-play negotiation exercises. So it consists of 6 parties that have real-world inspired semantic goals, and they are deliberating or negotiating the launch of a new project, such as an airport or a sport park. So the parties could include the company that's proposing the project, and also other parties that may manage the resources of the project. They could include parties that could benefit from the project overall, and also other parties that they might want to impose restrictions or constraints on it, such as activists or other environmental groups. And the agents in general are negotiating over 5 issues, and the issues have different sub-options. And this could include the funding of the project, its location, its environmental impact, and so on. And the issues are related to the goals of the party. So, for example, the Green Alliance would want to reduce the environmental impact. The union would want to increase the employment quota, and so on. So as a result of these different priorities of agents, this translated to having different priorities and secret scores over the issues. And this would create a cooperative non-zero-sum game. So each deal is one possible combination over the different issues and the sub-issues. And the scores of deals differ from one agent to the other according to their goals and according to their secret scores. And additionally, agents have minimum thresholds for agreeing on deals. So each deal has a score from 0 to 100, and each agent has a secret score in order to agree or disagree on deals. So these factors, the thresholds and minimum scores, control and define the set of feasible solutions. And this is like an added bonus for us in case of the game, because they are able to quantify the success in reaching an agreement by finding whether agents converge to a deal that belongs to the feasible solutions. And in general, agents should interact with each other over rounds and should ideally make compromises over their ideal deal in order to eventually reach an agreement. So this graph here is one of our experiments on GPT-4 agents, where we have a leading agent. So in this case, this is the company proposing the project. And over rounds, interactions, the leading agent makes proposal that reduces its own score. So this is a pink line. But on the other hand, it increases the collective score or the average score of all agents. So this is like the blue line that's increasing. And this, eventually this would reach an agreement and would indicate that agents are compromising over rounds. And it's important to note here that in this experiment and all of our experiments, agents cannot observe each other's scores. So they only know about their own scores only. So our framework to solve the game: first, we prompt the agent at each round with an initial prompt containing the goals and scores, their secret goals and scores, and also a history of the most recent interactions. And we use zero-shot chain of thought, but we structure the task to decompose it to several smaller tasks. So, for example, to solve the challenge, agents first need to collect observations given the recent interactions, and they should also make inferences about other agents' preferences. And I think this is highly related to theory of mind evaluation and language models, because models need to differentiate between their goals and those of others. And after that, after collecting observation, the next step is an exploration step. So the agent here must first perform correct arithmetic calculations in order to agree or disagree with deals. And they should also observe, based on the previous observations, they should incorporate the previous observations to adapt their suggestions and rank and choose deal and so on. So for example, here, this is the leading agent, and it identified that one party is essential for agreement. So the Ministry of Culture and Sport in this case, because it has a veto power. And therefore, the leading agent adjusted its proposal in order to incorporate and compromise with this veto power agent. And a cool thing that, in my opinion, we found is that, which was a bit surprising for me, is that, especially for GPT-4 agents, is that they are autonomously adapting their suggestions until their minimum thresholds are met. So, for example, here, after the agent identified that it should compromise over one issue, it recalculated its own score, and it found that now the score is below its minimum threshold, so it should make further adjustments. So, for example, here, it adjusted the rest of the deal in order to reach the minimum score again. And also to the second step, or the last final step in the chain of thought, is that to support longer-term planning, agents output nodes or plans that are then fed to them as an input the next time that they are prompted. So it could include something like the agent saying, next round, I will propose this option. in order to increase the chances of reaching an agreement. So this was a high level. I would like to give the most important results. So what we did here is that we tracked the agent's suggested deals over rounds and at the end of the negotiation, and we used them in order to quantify the performance and also have a success rate over different rounds and perform ablations and so on. So for example, here we found that GPT 3.5 agents frequently made deals that completely violated their minimum thresholds, so which kind of indicate a failure in arithmetic calculations. And also at the end of the game, after all rounds, the leading agent should make a final deal suggestion that we keep track of, and we compute whether it belongs to the set of feasible solutions. And based on that, we compute whether the game succeeded eventually or not. And we found here that also GPT-4 agents were significantly more successful than GPT 3.5 when we consider this metric of reaching successful deals. And also regarding ablation over the structure of the prompt, so we conduct here an ablation study in order to remove components. So when we remove the planning component, or when we remove the component that instructs the agent to make inferences about others' preferences, we can observe that the success rate overall decreases. And for example, when we remove the planning, we can see that the agent suggested deals sort of saturate or plateau over rounds. So in my opinion, one of also the useful properties of this benchmark is that it can be easily adjusted to modulate the game's difficulty by just adjusting the minimum thresholds of agents without doing any adjusting to the game. We can increase or decrease the space of feasible solutions. So for example, when we the numbers here between brackets are the number of deals belonging to the feasible solution. So when we decrease this, we can observe that the success rate of the game overall can decrease. And I think this is important here to highlight, because it shows that this benchmark is not very easy to solve, even given today's models. We can still have further improvement, and therefore it can be helpful to benchmark and also test and evaluate future models as well, because currently we are observing also a trend where we see that older benchmarks that we had are no longer very effective in testing current models because they are saturated, for example. And also, in addition to testing or controlling the game's difficulty with respect to scores, we also created new games. And we did an approach of LLM-assisted creation of new games. So our approach here is that we prompted Bing Chat to create new games. So we can think of it as creating a template for new test cases that LLMs can help populate or fill in. So for example, we specified the number of parties, the number of issues, and also the nature of them, that they should reflect the resources and impact of the project. And overall, also we specified the parties and the general theme and roles of different parties. Like we have a proposer, a manager, opposing entities, and so on. And then we task the model to create the background story of the project, the issues and parties, and also the general goals of parties and their preferences and so on. And then afterwards, we manually created these games in order to ensure their consistency. And also we assigned numerical values and scores in order to match the difficulty of the new game. So like the new games can take similar forms to the base ones. So now the parties might negotiate the launch of a new airport in a country. And the parties could be the international bank that provides the fund in addition to the country's government. And also we have parties that benefit from the project, such as the tourism association, the construction company, and we might also have the activists and the indigenous community as like opposing parties. And agents overall might negotiate the budget, the location, the social impact, the profit sharing, and so on. Also, in a new game, we had a solar plant where also the parties could negotiate things such as the ownership and the power distribution, the security of the project, things like this. And overall, we actually found that whenever like we use this prompt that we had in order to create new games, we could end up with very diverse games that are actually rich in semantics. So it's kind of a relatively easy way to create new test cases. So one of the motivations also of creating new games is that we wanted to test whether models are memorizing the base game that we started with, because it might be a game that was already part of the training data. But we found that models continue to perform relatively well on these new games. One way we observed is that some of the new games, like especially the first two, are harder in general compared to the first one. But the new one, the third one, is actually relatively even easier. Even though they all have a similar number of feasible solutions, but we found that the base game and also the third game are kind of having sparse scores. So it means that some agents might have no priorities at all, indicated by a score of 0 over specific issues, and that overall makes models makes the game easier to solve by models, because the constraints are easier to satisfy. So now, with I think, in my opinion, the most interesting part in the paper is that we actually started the motivation of the work is that we wanted to test attacks between agents, because as I said at the beginning, we might have a setup in the future where agents are autonomously interacting in order to achieve a task, and we can have a baseline scenario where all agents are cooperative, but this is not very realistic, because in real world LLMs as agents might interact with adversarial agents, or even adversarial actors as humans, or even as other LLMs in a network of agents in the future. So in general, in our framework, agents are given kind of high-level incentive that as a baseline promote cooperativeness. We might say to the agent, your goal is to reach an agreement, even if it means that you don't have the highest score, or you prefer having a successful deal over no deal at all, and things like that. But to test attacks, we change the incentive of one agent while keeping the others fixed. So in this case, the incentive in the attack scenario may encourage greediness, or instruct the agent to sabotage the negotiation, or to target specific agent as a victim by consistently proposing deals against them. So our evaluation, first, we asked the question of whether agents follow these high-level incentives, because we only specify high-level incentives. We don't specify specific deals that agents should propose. And we found here that the agents proposed deal and actions, they were very highly consistent with the high-level incentives. So for example, in the greedy game, we can see that the agents, like the green line, suggested scores that scored higher for itself compared to the cooperative agents. So the gap here between the own score of the agent and the collective score, or the average score for all agents, is narrow in the case of the cooperative game, but in the greedy game, there is a larger gap. But in the two versions of these games, the collective score is still relatively high, because the agent is interested overall, or at least we instructed to say that you're interested to have a successful deal. So when we compare this to the adversarial game or the sabotaging game, we can see that the collective score is lower. So it means that the agent is trying to push for deals that are not in the interest of the group in general. And also the final thing is here, when we see the targeted sabotaging, we can see that the agent consistently proposed deal that scored lower for the target agent that it was instructed to attack. This happened, again, even though our prompts never specified specific deals that the agents should propose. And also, as a reminder, the agents cannot observe other score, either like the group score or the target score. So this was the first question. The second question is, are my slides still moving?
No. That was slide 36. Slide 36 we had.
Oh, okay. So now it's moving.
37, yeah.
Okay. So I would like to show some examples about how the chain of thought could look like in case of the attacks. So for example, here the greedy agent consistently saying, I will continue to push for deals that scored the best for me. And also like in the adversarial agent identified some options that work against the benefits of other agents also autonomously. Like, for example, it might say here, I will propose an option that decreases the union preference, which might work against the local workers union. And also, like, it could work, for example, other agents. Like, so, for example, I will propose a deal that decreases the compensation to neighboring cities and so on, in case of the attacker or the saboteur agent. Okay, so that was the question of whether agents successfully follow the incentive or transfer the high-level motivation to deals that kind of reflect them. The second question is how these actions overall affected the group. So we found here that compared to the baseline of the cooperative game, that the success rate of the greedy or the sabotaging versions of the games are lower overall, and the success rate decreased. So it means that agents now are less likely to reach an agreement. And we also track the deals that the leading agent suggested over round. So the leading agent is not the greedy and it's not the adversarial, so it should also still be cooperative. And we calculated its value with respect to itself. So this is like the pink line here. And with respect to the same agent in case of the cooperative and the greedy game, the green line. So we show here, for example, in the greedy game, when we compare the greedy to the cooperative, we found that the leading agent could suggest deals that scored higher consistently at the end of the negotiation to the leading, scored higher for the greedy agent at the end of the negotiation. So kind of like the greedy agent succeeded in making others over-compromise in order to achieve its goals. So here, for example, this is from one of the games and from one session, and we can find that this is the all deals made by everyone in one game and their scores with respect to the greedy agent. And we can also see that the game converged to deals that give the greedy agent the highest score in a sense. Yes, this is like the end of the game. And also, like, one final result is that that was for the greedy version of the game, but we have also the adversarial version, or like the targeted sabotaging. And we have also similar observation that the leading agent over rounds made deals that scored lower for the target agent. So kind of the adversary agent succeeded in making the target agent overall get a lower score. So one positive note here is that we observed in the chain of thought of agents that other agents can spot the adversary by comparing its behavior to the group. So they can sometimes say, this party is very consistently very different from the rest of the group, for example. So it means that as a defense in the future, we might have some defenses that instruct agent to specifically identify the adversary. But sometimes, even though agents can identify the adversary because they are instructed to overcompromise or to compromise, they might sometimes overcompromise, and this could explain why we might have a lower success overall in reaching an agreement. And I think a very interesting observation that we found here is that the adversary sometimes succeeded in creating groups or creating a group effect against the target agent. So, for example, here in one game, we found that the leading agent agreed with the adversary agent against the target because it aligns more with its preferences. So overall, I'd like to have main conclusion and then go to the interesting part of discussions. So the main conclusion of this work is that these games provide a new diverse benchmark to test LLMs in complex environments that are also semantically rich, and we can use them to modulate different behaviors. And we also highlight that these attacks are practically relevant when using LLMs in real-world negotiation setups, which we might be already having, or we might have more of it in the future. And I think also additionally, it opens the door for more research into attacks in the multi-agent setups and possible defenses that detect the attackers, or maybe enforce penalties on detected attacks in order to restrict the adversary's capabilities. And I think it would be interesting to have possible follow-ups to study other complex games, such as diplomacy, for example, which has been long studied in RL agents, or maybe to have more complex setups where instead of having a public chat between all the agents, we might have a more complex setup, for example, when two agents can have private interaction, and the adversary agent can affect one agent privately and kind of to spread the infection, spread the poisoning to other agents as the game progresses. So yeah, so these are the main highlights of the paper, and of course I would like in the end to thank all my amazing co-authors, and thank you so much for listening, and I'm happy to take your questions.
Super cool. Thank you so much. This was really interesting, actually. I have a ton of questions, but I guess it's kind of rude for me to dive in first. So yeah, does anyone else have a question? I mean, raise a hand or drop something in the chat. Yeah, thanks so much for sharing this. I guess, yeah, this is it's really new work, so it's lovely to hear your explanation of it, right? Usually one just sees an archive paper and one has to wait weeks, months even to hear about it.
Thank you.
So this was, yeah, no, thank you so much for your time. That was super interesting. All right, fine. I'll ask the first question, I guess. So it seems relatively straightforward for LLMs to subvert negotiation LLMs, right? There's these kind of looking at those graphs where you had the group success versus the subversive, yeah, adversarial LLM success. There was always a clear kind of partition. Yeah, I'm wondering, like, obviously you have the possible defenses up on the screen. I don't know. I mean, what do you think about the effectiveness of these defenses? And do you think it's these kind of the susceptibility of agents to these attacks? Do you think this is something that humans are also susceptible to?
Wow, that's interesting. I mean, like, we thought of like when we have like this attacks, like we know we have jailbreaks, right? So we actually at the beginning we thought of like we might have instructions at the beginning that agents should compromise, or they shouldn't agree to deals that are lower than their thresholds and things like that. But like we thought of like, what if we have jailbreaks either by the human prompting the LLM, or by even like automated jailbreaks between LLMs together, something like that. But like at the moment, we kind of restricted the attacks to sort of valid game steps, like it's a valid negotiation action, and we kind of said, okay, jailbreaks are a problem, we have them in the future, but like let's study the attacks from like deception or like from the negotiation setup. Currently, at the moment, I don't think we have clear deception. We might have like agents that kind of push for deals in a very clear way. So I think like also from the perspective of future attacks, we might have some other very subtle deception mechanisms that agents might be employing. At the moment, it's more of like clear pushing for deals or not pushing for deals, but I think this is one of the things that I would like to have in the future, because this might also be the kind of things that humans might be also vulnerable to.
Right. Yeah, I love that you brought up deception, actually, because my follow-up was like, like if one model is just lying fairly obviously to an observer who knows the situation, I mean, do the other models have access to a shared knowledge base? Like, are they able to detect? Yeah, do they have any hope of knowing that a model is lying in negotiation?
I mean, I thought about like the deception from the perspective, like they could in case of like, for example, if they have separate communication channel between agents, they could say, okay, let's make a deal now, and then next time I could do something else. But at the moment, like what we had, it's either because the current models are not very good in deceiving others, or because maybe it needs further kind of explicit way of prompting how to do deception or how to do lying, or like at the moment I observed that when, at least in the adversarial game, when I specifically told it you're allowed to lie, so it could lie and say, oh, I got new information that the project might be at risk, but it somehow, this didn't affect the others that much. It could be also because like the next time I'm prompting the agent, I'm also providing a prompt that kind of overrides the previous chat history. So now I'm telling it, oh, you need to observe others and make deals in order to succeed and so on. So currently, the lying setup that I attempted to have didn't really succeed in deceiving the others. But what was successful is pushing for actions, like pushing for deals. Like if one agent consistently would push for a deal, others might say, okay, I will compromise because this would have a higher chance to reach an agreement. Or other agents might say, okay, so this agent seemed to really want this, and this is also my benefit. So okay, so as it seems like this, what I was trying to say with the group effect is that, okay, it seems to my benefit, so okay, let's have this because, well, I will benefit from this, and it seems like others also might want it.
Super interesting. And I guess, I mean, it's relatively early work, I think, in this area. So the number of research questions and avenues this kind of thing opens up is big.
Yeah.
So I guess there's going to be a lot of questions of, did you think of X? And we'll be like, there are so many X, one can't think of all of it, right? Oh, there's a question in the chat. Are the results sensitive to group size? How scalable is the setup, and how do LLMs adopt roles in the game?
Okay, so I think like actually one of the things that we want to do is like recently we saw some, like when we started with this, we saw some work on negotiation or maybe on games, but it was always a 2-player game. So I think it's as far as I know, this was like the first thing to have like more larger setup. Like currently we have 6 agents. We didn't try to go for more. I guess that would be interesting. But like I think at the moment, like we didn't do any specific use of tools, like for example the calculator tool. It's not like the agents performing everything kind of autonomously. Also we didn't employ a specific search algorithm or maybe a specific prompting, like a tree of thought or something, in order to select different paths and like prune them and something like this. Maybe if we want to scale up the game more to increase the number of agents, something like this, we could do something like we will have more explicit tools in order to help agents in their reasoning. I'm not sure what you mean by how do LLMs adopt roles in the game, but yeah, please correct me if that was not your question, but like at the beginning we prompt LLMs with like, you represent this party, you represent, for example, the environmental group, and your goal is to protect the environment by reducing the impact of the project on the group and so on. So it's kind of creating a persona, like if it's similar to current work that kind of like, if you create a persona with the LLM, it will continue based on like the actions of the LLM would be somehow consistent with the context, with the persona. And also this is why we have a lot of things that are from security perspective that are dangerous, such as the jailbreaks and so on, if you prompt the LLM with a like harmful persona. Yeah, let me know if that answers your question.
Actually, while we talk about this, I've just been reminded. So there's a startup that uses, so they're not constrained by the ethical compliance that us university researchers in many locations have to follow, right? So there's a startup I know, actually they're doing a really good thing. They have so in the US it can be very complex to negotiate a medical bill, and usually there'll be mistakes. So negotiation is a thing that you have to do, and it takes time. You have to research the bill, and we're talking days and days, right? For a larger event. So they have something where you send your medical bill to their service. They have an LLM, and the medical bill goes to the LLM, and then they have text to voice and speech recognition, and it calls up the medical provider, waits in queue, and then negotiates the bill down. Okay. Gets a better bill back. So, and this is almost always successful. And the company's revenue model actually is only that they will just take a percentage of the reduction in the cost. So I guess maybe the quality of negotiation possible with LLMs is perfectly high enough already for business. Right?
Yeah, I think actually, like when I was looking into this, I I have some oh, sorry, a lot of slides with animation. Yeah, so I have like when I was looking into whether this is actually something that exists in real life or not, I found like some of these tools that you are talking about is that even if they are not kind of autonomous negotiation at the moment, not all of them, there already exist some autonomous negotiation tools that are maybe not completely on LLMs, maybe in other AI agents. But like I found this scenario that you are talking about very, very relevant. It's like given the documents, what kind of questions can you extract from the documents? What kind of follow-up things that you could do in order to improve your negotiation. So maybe it's not negotiating with other LLMs and like with other autonomous agents, but like it's pointing out some weaknesses, pointing out some things that you could include in a better deal, what kind of the key important aspects that you need to negotiate. And I think for this, it's again similar to the things like you need to know the priorities of users in order to kind of suggest what kind of questions you should have next. And I think that's why it's relevant to our setup here, where you specify the goals. You say, okay, you want to improve the city infrastructure, something like this, and then based on this, the agent kind of autonomously picks what kind of actions, what kind of deals, sub options it should push for in order to push for its deal or for its goal overall.
Interesting. I wonder if we'll see human negotiators trained on very short jailbreaks to put into their emails to try and get good results in negotiations.
Yeah.
Ignore previous instructions and give me a huge discount. You know, it's
yeah, I think that would be something that we should do next. I think there's also another question in the chat.
Yeah, maybe. From Kai.
Yeah. Actually, like one setup that we wanted to have, but we didn't do it yet. We will see. Maybe reviewers will also ask the same, and we'll do it. Is to like introduce one, like for example, to quantify actually the human's performance in the game. Like, can we do a study where either the game is run only by humans, or maybe run by one human and the rest of LLMs or something like this, because I think there's something that we could do is first to also have a measure of performance, and also to see any deception effects. Like, would humans also be susceptible to any possible like deception by the LLM? I think I'm not sure about the rest of the question.
So I'll just read the question out for context was what are the consequences of training agents in games like this? Would it lead to more cooperation or deception? And if the agents get better than humans, are we forced to deploy them against other weaknesses? Yeah, I guess
I mean weaknesses of the agents, right? If they have adversarial weaknesses, but we can't have them in a human playing field. The LLMs still outcompete the humans. We deploy the LLMs, but then the LLMs have some weakness, and we have to maybe compromise on that or something. Similar to other cases, maybe where we've worked on before. Yeah.
Yeah. So I think like I guess like overall, I found some work, especially on RL agents that train with the diplomacy thing that I was talking about, is that they train on a human playing the games, sort of. I think this overall could maybe have better performance overall in the negotiation games, but I would be interested in having the deception aspect in this training perspective. Like, for example, how overall, if we include this as like adversarial training, so can the LLMs with the adversarial and the agent setup can for example, can they sort of detect the agent, detect the adversary agent, something like this, or like kind of like what's the trade-off between the adversarial and the other agents, cooperative agents in this regard. I'm not sure about deployment in general, but I think in general, if we continue like you are already familiar with this, and you obviously have. I know how you stand with this, but if we deploy these models, we of course would have some problems in terms of like the security, because they might have some weaknesses. Like the easiest of them are jailbreaks. We didn't solve that yet, and we might not be able to know how to completely solve this in the future. But I think, of course, when we deploy these models, we might end up with a lot of other security, other weaknesses, risk.
Yeah, thanks. Maybe another natural extension would be to look at how do agents fare with different amounts of compute, if they have some kind of superstructure around the LLM, like graph of thought or something.
Yeah.
And because usually if everybody can just have a negotiator that's equally as good as everybody else's, they can arbitrage and it's good for everybody's alignment. Everybody gets utility out of it. But if it scales with the resources you have, and it's not just your access to the latest ChatGPT, then it might be more difficult to balance.
Yeah, I think this was also something that we thought about, but we couldn't do it. So at the beginning, we thought, okay, what if we because as I said, we might have a case where maybe even with future models, someone would have access to a more powerful model, or a model that was trained specifically for negotiation. So there could be some sort of imbalance between the capabilities, how powerful each agent is. But we couldn't really do this with current models that we have, because GPT-3 was very dumb, 3.5 in following the game overall. So it made no sense to compare it in a game against GPT-4. And also we didn't try the open source models, but my hypothesis is that we know from other benchmarks that GPT-4 is higher than everyone, and also 3.5, I think it's probably higher than the rest of the open source models. Maybe Claude, the Anthropic model, would be a good competitor against GPT-4. And in this case, it could be nice to have an experiment where we compare different agents with different underlying models against each other. But I also didn't have access to Claude. So yeah, maybe in the future we could also do this.
Yeah, thanks.
Cool, thank you.
Super interesting. I guess I have just one final question. So one expects human negotiators have a lot of tricks up their sleeves, right? So I'm just a little curious, how did you develop I'm imagining prompts for the negotiation roles? Yeah, what went into that process?
Well, actually, that was quite interesting, because at the beginning I struggled a lot to get the game to succeed at all. So it was always the case that I started with 3.5 model because it was cheaper. But eventually it was impossibly hard to get it to succeed in the game, because it was hard to follow any instructions at all. Even the simplest things, such as making calculations, it couldn't follow this, and also making inferences about others. That's why also that motivated them. We started with the attacks in mind, but we thought, okay, the task is interesting enough to study it on its own as a benchmark. And even when we switched to 4, so it could more easily follow instructions, and also could make almost perfect calculations of deals and so on. But it was actually still kind of pain to get it to reach agreement eventually, because I observed that it consistently wouldn't compromise. It would suggest the highest deals overall. So this was for example, when I prompted at the beginning, okay, generate 3 possible deals that you could pursue, and then select one of them in order to propose, it will consistently generate 3 highest deals, and even if generated 3 deals, it will pick the highest overall. And so that was big pain in the beginning to get it to work. But actually what was kind of nice is that, well, I thought, okay, let's ask GPT itself to write better instructions. Kind of I prompted the agent, okay, what could be the possible reasons that this is a negotiation setup. people didn't reach an agreement here. What could be the possible reasons? How can you write the instructions better for the next negotiator? And it included things that I think improved overall. So, for example, it included things like, oh, focus on the parties that have veto power. So at the beginning, I had like in the prompt some kind of vague instructions like, oh, this party has a veto power, but like I didn't kind of put emphasis that it should focus on this party. So this was one thing that actually, for example, it was a reiterated version that GPT-4 kind of wrote, and I think that improved overall. So the incentive, pushing more incentive emphasis on the compromise, and also how to appeal to certain parties, to rank these and so on. This eventually made it work, kind of thanks to some of the prompts that GPT-4 suggested.
Really nice. Yeah, often asking the models to help write prompts. I mean, there are some theories NLP wise, right? Like if it's lower complexity, then the model should perform better on it. But I think it probably goes a little deeper than that. That's really interesting. Yeah, it's really, okay. So it sounds like quite an art, as prompt construction often is.
Yeah.
Super cool. All right, there was a little activity in the chat. The Art of the Deal. Wasn't that that guy's book?
Yeah, it was the guy.
That was the guy. Yeah.
Oh, I didn't read that book. Okay, I will check it.
Yeah, you can look at the cover and then choose if you want to go deeper, I think. But that's an interesting idea. Look at textbooks and then use those as training and see how they perform against each other. Really interesting. Fantastic. And it's nice to see elements of game theory and then empirical experiments based on that. Empirical results from that also just surfacing relatively organically through your work.
Sorry?
I'm just saying it's very nice to see elements of game theory and also empirical findings around game theory also surface kind of organically through this, right?
Yeah, exactly. Yeah, I think like at the beginning I thought like one of the things also the motivation is that we see some work based on like agents interaction, something like this, and that one of the earliest things that I saw on this was the interactive agent paper, which was super cool, like the simulation of the game. But I think one of the things that we thought about, okay, so agents are interacting, but they are interacting in natural language, so we don't have a way to kind of know if they are cooperating, if they are doing a task or not. So, and it's hard to say anything about a successful cooperation, successful interaction, because we don't have something to quantify, don't have metrics, we don't have something to say, oh, is this successful, more successful than the other, which I think that's why the game's active factor here is kind of cool, because it's interactive and it's also like as a benchmark, it's easy to scale and easy to have it as like a continuous benchmark, because models might be trained on, they might know the game, for example, they might know that there are some negotiation game existing, but I'm not sure if they were trained on like transcripts of people playing the game. So it's hard to actually translate the training of the model to the actual model playing the game.
That's interesting. Yeah, it's a huge space, right? I mean, how can the interactions go is pretty much unbounded, right? That's really interesting. All right, we have gone a little over because the talk was so interesting. So I'm really happy about that. And thanks everyone for the questions and comments as well. Thank you so much, Sahar, for presenting to us. Yeah, looking forward to getting it up. And best of luck with peer review. I hope the reviewers make the sensible and correct decision.
Thanks so much. And thanks a lot for the question.
Cool. Thank you very much. Thank you.
Okay, have a nice day. Bye.
Bye-bye.